Now let's recap with irrational numbers because we're going to discuss about how we can identify a number to be irrational or rational, supporting through some of the theorems and properties which we're going to discuss out here. So before that, an irrational number is a number which is not rational, is how we understood the concept when discussed with the different types of numbers in real number system. So the numbers which are not rational, that is, the numbers which cannot be expressed in the form p by q, where p and q are integers and q not equal to 0, are called the irrational numbers. So mathematically, the irrational numbers are denoted with all real numbers except q, because we don't have the rational numbers included in irrational part. So excluding this, the remaining numbers in the real number system are called the irrational numbers. So coming to the irrational numbers, there are many example irrational numbers which we can discuss here, like root 2, root 3, root 5, root 7, etc. And root of a prime number is an irrational number, and pi, which we know, is an exceptional irrational number because this has its own history in mathematics. Then you can also take 0.010, etc. So I have different types of irrational numbers in mathematics. This being one of the case is how I understand the irrational numbers. Now let's see how we can identify a number to be irrational. Why do I call root 2 to be irrational number? There should be a mathematical proof valid for that. So is what we're going to discuss in today's session. So before that, there is a very important theorem which connects the fundamental theorem of arithmetic, and let's see what the statement says for the theorem. So if I consider the theorem which says that let P be any prime number if that prime P divides a square and a belongs to positive integers, z plus is positive integers. If P divides a square and a belongs to positive integer, then P divides a. This is a very important theorem which is helpful in identifying a number to be irrational or not an irrational number. And the statement, when I read it, says that for any prime number p, if p divides a square, for a being a positive integer, then p must divide a, is how I understand the statement of the theorem. So to go with a small short note on the proof of this theorem, let me start with the proof, where I take let p be any prime number. Then let a belong to z plus is what I have considered here for this positive integer, such that we have already discussed in the prime factorization method the fundamental theorem of arithmetic, which stated that every number can be expressed as product of distinct or not distinct primes. It can repeat, but it should have product of all primes. So going by the fundamental theorem, such that by fundamental theorem of arithmetic, a can be expressed as product of p1 times p2 times p3, so on and so forth, pn minus 1 times pn, the product of different primes, where each of this need not be distinct because some factors repeat, where p1, p2, p3, pn minus 1, pn are distinct need not be 2. So these primes are distinct or may not be distinct because sometimes they repeat. So are distinct or need not be distinct primes. So for these different primes, I have A which can be expressed as P1 times P2 times P3, so on and so forth till Pn. Now using this, my statement says that if P divides A square, so let P divide A square. Divides is the symbol which I use as a sign as a straight line. So this symbol indicates that P divides A square. That implies P divides A square, which can be written as P1, P2, Pn whole square. So because A is P1, P2 till Pn, I square it to get this. That implies P divides P1 square, P2 square till Pn square. So P divides this. So as you can see here, I have considered the case where P divides A square. Now because A square is P1 times P2 times P3 till Pn, therefore that implies that P is one of the factor of A square. Now when I say a number divides another number, that number is said to be one of the factor of the given number. So if I say A divides B, A is one of the factor of B. Therefore P divides A square implies P is one of the factor of A square. But A square is already with different factors P1, P3 till Pn. Therefore this P must be one of the P1, P2, P3 or Pn. When I take the square separated. So when I substitute here, since P is one of the factor of A square, that implies P is one of the factor of P1, P2 till Pn. But P1, P2 till Pn are all possible factors of A square. That implies all possible factors of A square are P1 to Pn. It cannot have anything other than that. But when I say that P is one of the factor of A square, that means P should be one among P1 to Pn, because these are the only factors available in A square. Therefore, which concludes that P is one of either P1 or either P2 or either P3 or either Pn. Therefore, P should be one of them. That implies when one of them is P out of these, which is nothing but A, when multiplied becomes A, that means P must divide A because P lies in one of these products. If it lies somewhere in between, then this clearly indicates that P divides A because P is one of the factor in A. A expressed in the form P1, P2, P3 till Pn is how we understand the concept of division and the factors. So P is one of this. That implies A equal to P1 times P2 times P3 so on till Pn continued here implies that P divides clearly A because P is one of P1, P2, P3. So it must lie in between either P1 to Pn, somewhere in between. Therefore, P divides A. Therefore, the proof. So P divides A is what we get in the statement. Therefore, when I consider any prime number such that if P divides A square for any positive integer A, then immediately